And so we're going to study lengths of curves, both in R2 and in R3. Okay. So here we go. Well, okay. The arc length, which we use the letter S for arc length, along the smooth curve do you guys know what I mean by smooth? What's that? Differentiable is a nice way to say it. Maybe it has to be differentiable twice, is what they used to tell me in my differential geometry class. Sometimes you need the first two derivatives to exist. If you have a cusp, we know we're not differentiable at a cusp. So we like when the wire is bending, but we don't like when it gets a kink in it. That ruins all my differential geometry. Okay, so along the smooth curve, and let me make it r of t equal to, well, again, x times vector I plus y times vector j plus z times vector k. Well, between the points r of A and r of B is given by that formula I just had. So I'm going to write S is equal to integral A to B square root x of t squared plus y of t squared plus z. Oh, wait a minute, there's something I'm missing. Did you figure out what I'm missing that was in the reading? This should be prime, x prime of t, y prime of t, and z prime of t. So we're going to need to take derivatives. Okay? And then we're going to work out what we have. So one thing about this formula is it's nasty. Well, what I mean by that is, example here, suppose you have r of t, so let's say if r of t is equal to, let me use the other bracket notation because it's a little bit quicker, t squared and t cubed. All right. Then what do we get? We get S is equal to integral A to B of the square root of what? 1 plus 2t plus, wouldn't it be 3t squared at this point? Oh, we need to square each of these things, you're right. So it's 2t quantity squared and then 3t squared quantity squared dt. Yeah. So what's that equal? That's the integral from A to B square root of 1 plus, like you said, we want 4t, this is t squared, and then plus 9t to the fourth, right? dt. Yeah. I took Calc 2. We didn't have to integrate that in Calc 2. Right? I think you did some integrals where you had square roots. But, yeah, Sullivan?
This looks a lot like the arc length formula that we got in Calc 2.
It's the same, The only difference is we added a dimension, right? So it shouldn't surprise you. That was one reason I said I'm not going to derive it. You already did in Calc 2. Yeah. Calc 2, this is just, I mean, you could say that this formula, what's the general formula, right? What you're really doing when you do the arc length is you're integrating from A to B the length of r prime of t dt. Right? You're integrating the length. Guys, think of it this way. The integral symbol, that means the limit of what? What kind of sum? The limit of a Riemann sum. When they were dividing up into subintervals, you had lots and lots of little tangent lines added together. Well, then if you do it infinitely, you integrate the length of those tangent lines, and that gets you the arc length. Okay, so I guess this is not a surprising formula. But I'll also say that in general, we cannot compute these integrals. Okay, that's great. So what do you do? Well, if you can't compute them, can we approximate them? My TI calculator can I could put this in the TI calculator. You guys ever seen it do that? Sure. You have the curve, you put it in there, you say integrate from A to B, and it fills up goes across, then it spits out a number, right? How does it do that?
It breaks it into really, really small, but not infinitely small rectangles.
Rectangles, yep. Left sum, right sum. Or there's better ways. Trapezoid. Do you guys learn about the trapezoidal method? And then there was something even better called Simpson's method. Simpson's method is actually used. And there are better methods, and if you're interested in that branch of mathematics, that's numerical methods. Okay, numerical mathematics. So we can't compute these in general, and so, you know, I guess if your book has a little T next to it that says use technology, please do it. Don't sit there and try to think of a really cool trig substitute. Oh, you can if you want. I mean, just don't spend too much time. So I'd like to give you 3 that we can compute. So here's a partner exercise. So with a partner, please compute the arc length of these 3. Okay? I'm not going to give you t squared, t cubed, because that doesn't work. Oh, I guess something else I'll have to give you is I'll have to give you A and B. I'll have to tell you how far along the arc do I want you to do the computation. All right, so we will name these R1 of t, R2 of t, and R3 of t. 3 different exercises to try. And what I'd like you to do, I guess for each of these, step number 1, I want you to compute the arc length. You have a formula for it, so we just want to make sure that, hey, when you leave today, you can actually get 1 or 2 of the exercises on the homework correct. Okay. And then step 2, I would also like you to, if you can, this is just good practice for us, sketch the curve in space. The reason I mentioned GeoGebra is because when the examples get tougher, that gets difficult. And you can, did you guys see the baseball problem? I tried to give that to you. It's on I emailed you the link. So, and if you accept my invitation, you'll all be part of our class in GeoGebra. Then you can view these things easily. So, okay, R1 of t is going to be, here's a nice one, t, t, t. And let's range from 1/4 less than or equal to t less than or equal to 1. R2 of t, let's do t minus 2, t minus 2, t minus 2. and I want 9/4 less than or equal to t less than or equal to 3. And then number 3, I'd like to do t squared, t squared, t squared. See how you guys handle that. And we'll go from 1/2 less than or equal to t less than or equal to 1. So I'm going to pause the recording, put you guys to work, say my hellos with an attendance maybe, and actually I'll come around and collect the homework while you guys are doing this, okay? And that way I'll have it all. I can check it during the break. The story is this, okay? In this problem, we have 3 different, and the word is what I used last time, parametrization. What a great word. You can't even use that in Scrabble, it's too long. Parametrizations of the line from, well, like you guys told me, 1/4, 1/4, 1/4 to 1, 1, 1. We have 3 different parametrizations. 3 different ways of traveling along the path. Okay? And that's really cool. You know, when you talk about the planets and we worry, everyone ever get worried when you're little that Neptune and Pluto may collide someday? I did. Because I learned, well, maybe I'm just kind of weird, but I learned that sometimes, right, at some point, Neptune was going to be farther away than Pluto, and then it was. Probably some of you, when you were thinking about these things, Neptune was farther away. And now I think Pluto's farther away again, if I remember my NASA stories correctly, right? But maybe I don't have to worry just because they, right? I mean, you'd have to be really unfortunate to get these things to collide, right? They'd have to be in the same plane, and they'd have to be hitting, more importantly, at the same time. Okay, the parametrization tells you something. This 4th dimension, this time, right? So, I guess what we learned from our little experiment, in addition to how to do the computations, is we learned, this take-home message, I guess, right, that arc length is independent of parametrization. That's really neat. And I'm going to say thankfully, right? Because if you were getting different answers for these 3 problems, we'd have to question our formula, right? You had to get the same answer for these 3 if you knew what it was you were actually computing. Okay? And I guess the other thing I mentioned is that's important is that the integrand of the arc length formula is, right, the length of, well, really it's, when I say the length of r prime, maybe what I should say is that's the speed, right? What are you integrating? You're integrating the speed. And you get the arc length. So that's kind of interesting. I mean, it came from the distance formula. There's a Riemann sum going on. We talked about all that today. So I think there were some good things you learned in this first little half. Before break, I have one more thing I want to do. I want to write down the following idea. If I said, suppose I write s of t equals integral a to t v of t dt. Is that true? False? Does it make any sense? What does it mean? S stands for what? No, not position. We've been using R for position. Well, there's another issue, right? Okay, so there's two things going on here. S stands for arc length. I'd like to write arc length as a function of time. I'm basically, instead of having an endpoint B, I want B to be able to vary. And then maybe, since a t is here, I should really use a different variable here. Maybe I should use, I don't know, theta or something. Well, theta has implications too. I'm running out of variables. How about v of, here, we'll go Greek. Isn't it rush week for a lot of universities? I heard this weekend. Anyways, v of tau, d tau. We'll honor them. Okay? But what Kathy said is also important. Wait, we were supposed to have absolute values for this formula to work. So let's also let's suppose that v of tau is greater than 0 for all tau. Is that okay? Well, I just want to suppose this. Suppose you have a positive velocity. Now I got to think about this.
What would the magnitude of the derivative of the position vector?
Yeah. I think I need them no matter what. All right, let's do that. So then I get this for free. Okay. So what happens then? By the good old fundamental theorem of calculus, yeah? Where'd you learn that? Calc what? Calc 1, right? You learned there were two parts of the fundamental theorem of calculus, right? The big one was, if you want to integrate, it's just big F of B minus big F of A. That's part of it. But the other part is this, that you can take the derivative of these area functions, we called them in Calc 1. You can take the derivative of an antiderivative function. So by the fundamental theorem of calculus, we would get, let's see, what's the formula then? ds dt, right, the derivative, s prime of t, has to equal what? Oh, I can see they did a great job of teaching a fundamental theorem.
S prime of t has to equal v of t?
Basically, yeah. And we decided we need absolute value bars. I agree.
Okay.
V of t. You just replace the tau with a t. Remember, the derivative of the integral is just whatever you were integrating. That's basically what it says. The fundamental theorem of calculus was this idea that we can undo each other, in a sense. That somehow the total the rate of change of this function is what you're integrating. So now let's suppose if the absolute value of v of t is greater than 0 for all t, we already know it's greater than or equal to, then what can I say about s of t? If the absolute value is greater than 0, that means ds dt, the first derivative of s, is greater than 0. Time out. This v, I understand, is a vector, right? I understand that. But is s a vector or is s a Calc 1 problem? It's a scalar, right? It's a Calc 1 function. Even though it's a really weird one. It's just a good old Calc 1 function. So you learned this. What does it mean when the first derivative is positive? S of t is increasing. S of t is increasing. If S of t is increasing, So it is 1 to 1. Do you remember those words in Calc 1 somewhere? No? Oh, yeah? What? Do you know what they mean? I don't know. We've heard them. Oh, we did that, though. We did that. If you have an increasing function, you're in good shape. So S of t has an inverse. Oh, yeah, I remember that because in Calc 1, or even in trig class, we had the cosine function, right? And the cosine function, if we wanted to take the inverse, we had to restrict the domain to go from just like 0 to 2 to pi. You guys remember that? And then for sine, you had to go from negative pi over 2 to pi over 2. Why? Because when you take an inverse, you switch the input and so you're switching x and y, and if we didn't restrict to just the pink, then we would not meet the vertical line test when we got to find the inverse. So you have to be 1 to 1 to have an inverse. Yeah? It's a lot of old stuff. If S of t has an inverse, then we may write t as a function of S. T as a function of S? Really? Yeah, you can. And I'm just going to say that this leads to what is known as the arc length parametrization of a curve. And this is a really powerful idea. And important enough that if you look at the table of contents of today's lesson in your ebook, here, let me go back to it. Oh, yeah. By the way, I just noticed this as I was scrolling through while you guys were doing the problem. Wasn't this one of your homework problems last night, this ellipse? Right? And then they were doing the planets. Did you guys see this chart? I was talking about this yesterday. Look, they compute the eccentricities of the planets. Look how close they are to 1. That's really cool. I didn't know our book did this. And then, here's the other two sections besides arc length. Arc length of a polar curve, I didn't touch that yet today. We'll see if we have time. But I just talked about basically this third section. They do a lot of work on thinking about arc length itself can be a parameter. And I feel like there's a lot of good ideas here, but I also felt like I might be able to sum it up a little bit for you. Okay? And so when we come back after break, I guess what we want to, well, or maybe even next time, because I have some other things to do, we're going to be thinking about expressing curves as functions of S instead of functions of t. Can we do that? Yes, because of this discussion. Let me say it one more time. So far, when I've written down parameters, I've always written what here? T. And you guys understood that. And we like the variable t because it represents time. But since time can be thought of as a function of arc length, it makes sense. You could write x, y, and z as functions of arc length. And when you do that, you gain a lot of power over the curve. And there will be plenty of times that we say, hey, of all the different parameterizations we could possibly choose, let's choose to parameterize by arc length. And when we do that, calculations are really simplified, including this thing called curvature, which we want to study next time. Okay? So I guess that's about all I have for before break.